Okay, ladies and gents, this is the next section, 1.4, continuity and one-sided limits. I believe this section is being broken up into two different lessons. This is the first one. The second one will be next. This is just dealing with continuity and one-sided limits. The next one is dealing with the intermediate value theorem and the squeeze theorem. Okay, so we're going to do this one. We are going to determine continuity at a point and continuity on an open interval. And then we're going to determine one-sided limits and continuity on a closed interval. There's your homework, practice, whatever you want to call it, there on the right. So continuity at a point and on an open interval. We know about continuity last year. We had some definitions of continuity over 3 parts. We're going to talk about those now. From AB, we kind of drilled it in AB. It's not so much a big deal in the BC curriculum because this will probably not appear on your BC test. But it's still good and nice to know so you can get the multiple choice questions right where it appears. So for a function to be continuous, it has to be unbroken. That means there's no holes, gaps, jumps. We also can say there's no corners, right? That's another one we kind of talk about. In other words, you must be able to draw the graph of the function without picking up your pencil. Actually, no, what am I doing? What am I doing? I don't even know. Corners are fine. Oof. Kinks. What are we talking about? Kinks. No, that's for derivatives. What am I doing? I don't even know what I'm doing. What class is this in? Oof. No holes, jumps, or gaps. That sounds good. Oof. Man, I'm going crazy right now. You must be able to draw without picking up your pencil. So that's pretty self-explanatory. He apparently wasn't because I didn't know what I was doing. Here are 3 examples of functions that are not continuous. So f of c is not defined. So for instance, if I have a graph here and I have a function, but at some point there's a hole there. That means that is not defined at that value. So this is not continuous because you would have to go up, pick up your pencil, and then go to the other side and go on. Okay. Number 2, the limit is not existing. So what does that mean? That means something could look like this, and then something could look like that. So because the limit from both sides is not the same value, right? It's going one's above, one's high, one's lower. One's open, one's closed. So that means that limit doesn't exist. Therefore, it's not continuous. For number 3, this is the f of x. The limit of f of x as x approaches c does not equal f of c. What does this mean? This means, some example is, so for instance, say I have a graph like this. This is open, and then this right above it is closed. So the point exists, but the point is not on the actual graph of the function. It's just out in space somewhere, and your open point right there is not the point that we care about. So the limit is fine. Okay, this limit works, like at this point, it's right here, but the f of c does not equal that limit. And that's kind of our 3, I guess, definitions, or 3 points to the definition that we care about for continuity. Remember, this should be a brief reflection upon what we did last year. Function f is continuous at c if the following 3 conditions are met. 1, f of c is defined, right? So f of c is defined. So that's our very first one, or it just means it exists. Okay, it exists somewhere, like that last example I gave you with the this was open and this was, so that technically exists, but then it fails on the other 2 and 3 steps, right? So that's step 1, or part 1 here. Number 2 is the limit of f of x as x approaches some c value exists. Now last year we talked about the limit as x approaches c from the left of f of x equals the limit as x approaches c from the right of f of x, which is equal to the limit as x approaches c from both sides, right? So the left has to equal the right, which, because those 2 are equal, it has to equal from both sides. So that's all this is saying. I just kind of cleaned it up a little bit, but that's all it's saying. And then number 3, that the limit as x approaches c from both sides of f of x has to equal f of c. All right, that's the 3rd step, and again, we need to know that. We can prove that, hopefully. We did pretty well on AP test last year, so that's nothing new. So continuity on an open interval. So a function is continuous on an open interval open interval, AB, right? It's open, if it's continuous at each point in the interval. A function that is continuous on the real line, or the entire real line, negative infinity to infinity, is just everywhere continuous, or continuous everywhere. Okay? So some examples. What the heck does this mean? So some examples are, what does this graph look like? Well, this graph is a rational function. It looks like this. So right there, right there. So this is continuous everywhere except 0. So this is continuous everywhere except when x is equal to 0. Another way we could say this is, technically 0 is not in the domain of this function. So it's from negative infinity to 0, open bracketed, right? And then open bracketed. So we can say it's continuous on its domain. 0 is not technically in its domain. Number 2 here. This x plus 1 when it's less than 0 is just a straight line till x plus 1. And then x squared plus 1 kind of comes like that as a parabolic function. And so this is continuous everywhere. I can't spell. Because I did not have to lift up my pencil to really draw the rest of that graph. Yes, this is a closed dot, so that's good. If it was open, that would not be good. If this was just x is less than 0, not less than or equal to, then that would not be a continuous function. Well, what about number 3? Okay, this function actually looks. We'll not draw that. But in this case, so so we can draw it. So this is really x plus 1, x minus 1 over x minus 1. These are going to cancel. So this function really just looks like x plus 1 all the way through. But when x is 1, okay, when x is 1, there's a hole there. All right, so this is continuous everywhere. O-U-S, U-O-U-S, O-U. U-O-U-S, U-O-U-S, okay. Continuous everywhere, except when x is equal to positive 1. Just because that's where the vertical asymptote, or not vertical asymptote, that's where the, what we call, oh my gosh. That's where the hole is going to be. Holy cow. These terminologies, oof, not good here. Okay. So if a function is not continuous, then we call it discontinuous. Discontinuities come in 2 types, called removable and non-removable. A hole is called removable. Removable discontinuities could be made continuous by appropriately defining f of c so that the function is continuous. What does that look like? So a removable hole, or a removable discontinuity, is like something like this. So I have a function kind of going up, and this is closed, but then I have this function kind of going that way. So this is a non-removable discontinuity. Or another example, this might be more familiar, is so if I have this one and then I have that one. So they're both coming from positive infinity. One's going up, one's coming down from positive, but that's called a non-removable discontinuity. A removable discontinuity is just a hole within the function. So if I have a hole right there, that's a removable discontinuity. The graph that I just had was x squared minus 1 over x minus 1, and this is also a removable discontinuity. I'm going to graph that function for you just so we can see what it looks like, just so I can pull it up. But I think, hopefully, come on, computer. There we go. There we go. All right. Let's finish it. I don't know why I got to do that every time, but I got to apparently. Okay, so let's go to y equals, we'll go parentheses, so is it x squared minus 1, x squared minus 1, close, divide, open, and then x minus 1. Alright, and then we will go to our graph. So again, it looks like a line, but if I go to the table, I might have to fix my table. No, I did, okay. When I go to my table, at 1 it's an error, right? That's your removable discontinuity. If I were to fix the domain a little bit and defining f of c Okay, I can definitely get rid of that hole. All right, fantastic. One-sided limits. Let's go. Piece of cake. A limit can be evaluated from just a single side of a point C. So left hand versus right hand. Okay, the right hand evaluates the limit as the function approaches C from the right. So my right is this way, but your right is this way. So it's coming this way. And then the left hand evaluates it from the left. Hopefully I did that right. Hopefully when I mirrored everything, it worked out right. One-sided limits can occur where normal limits do not. An example is right here where we have a jump discontinuity, right? So the limit from the left and the limit from the right exist, but they exist at different values. So the full limit doesn't exist. So let's get through some examples here. The limit of f of x as x approaches 3 from the left. So 3 from the left, it's approaching this way here. So that's going to be at positive 1. Okay. It's approaching 3 from the right. So this way we're going up here, and it's approaching 4. The limit as f of x approaches 3 from both sides. Because these sides do not exist, or they're not the same, that means the limit does not exist. Okay. And f of 3 is just 1. That's where the dot is. That's just 1. Okay. Let's evaluate those following limits on the bottom. All right. So, how do I do this? Well, yes, we're evaluating from the left side, and really, I can think about what this really means. Okay, I can just plug in. This is the same thing as just plugging and chugging, but if the denominator equaled 0, then I would have to do other things, like in part B and part C. So this one here I can just plug in. So this is just 3 times 2 over 2 plus 4. So that's 6 over 6. So this is 1. So the limit on that one is 1. This one, if I plugged in, I would get 3 minus 3 over 9 minus 9. So that's 0 over 0. Later on, you might be using L'Hopital's rule on that one. I probably would. But I'm going to show you kind of how to do that. So what I would do is I would take the limit as x approaches 3 from the right of x minus 3 over x minus 3, x plus 3. We got to realize that this can be factored. So now I cancel, okay? So it's the limit as x approaches 3 from the right of 1 over, right? The 1's still there, 3 plus 3, which is 1 over 6. So that's how that one's taken care of. This one is not going to be good because we don't really know how to deal with this one yet. This is going to be really just negative 1 over 0, so there's an indeterminate form. Actually, it's not even indeterminate. I can't even do L'Hopital's rule on this one, right? What does the graph look like on this one? The graph looks like this, and then it looks something like this, maybe. All right, so if I'm approaching 0 from the right side, what's actually going on? I'm actually going to get negative infinity. Okay, or it actually does not exist because it's not going to a whole number. So that's actually a better for does not exist, but negative infinity would be okay there. So just be aware of that. Make sure you know what the graph looks like before we get into what your values are, what your answers are. All right, let's try to finish this sucker up here. Okay, existence of a limit. Now, this is kind of like the second part of the continuity definition. If the limit as x approaches c from the left of f of x is equal to L, which is then equal to the limit as x approaches c from the right of f of x, then the right hand and left hand limits equal each other. Now that's pretty self-explanatory. You might be like, well, that doesn't make any... That's why we need that. Well, it's just there just to make sure we have it. You know, math is all about proving things and getting things correctly. Why does 1 plus 1 equal 2? Well, it does because it just has, right? We have to prove all that stuff works. So that's kind of how math works. We can't just take everything for granted. So here's another definition, just real quick. The function f is continuous on the closed interval a to b if it's continuous on the open interval a to b, if the limit of a from the right is equal to f of a. So that means that if I plugged a into the function, there cannot be a, like this has to be closed, right? It can't be an open hole and then another closed hole somewhere else. And then this cannot be open, and then this cannot be like a closed hole somewhere else. So because it's continuous from the right at A and then continuous from the left at B, we'll say that function is continuous on the closed interval A to B. All right, it's pretty self-explanatory. It makes a whole bunch of sense. It's, you know, it is what it is. Like we just gotta have it down. Okay, that's done for this video. This probably was a little longer than the first two, but not too bad. Let's go into the next video. Deuces.